x squared times 1, 1. Well, that's not especially interesting, but that would still be equal to partial squared f partial x squared times 0, which is 0, of course. But if f is complex differentiable, then, you know, this is really partial squared f partial y squared. And, of course, that's still partial squared f partial x squared equal to 0. I mean, really, the direction logically is more kind of upwards, but I'm showing you how we can also derive a partial differential equation on the basis of an algebra equation. You see, this algebra equation corresponds to this partial differential equation. And so that's the partial differential equation which is characteristic of the complex algebra. That's, of course, the Laplace equation. Of course, there are other versions of the Laplace equation. They all come from playing around with the Cauchy-Riemann equations and using the symmetry of the partial derivatives, right? It's no accident that I had to use the symmetry of the partial derivatives to get at this. But on the other hand, this is true for the complex function. And well, we often see this in terms of the component functions, right, of the complex function. So we'll see uxx, well, I'm sorry, uyy, right, plus vyy equal to 0, and oh, I'm sorry, u, my current notation, and good grief, vyy plus vxx equals to 0, right? Those are the Laplace equations. They hold for both components. What else then? Well, you know, if we look at the algebra of the hyperbolic numbers, well, there we have E1 equals to 1, we have E2 equals to j, and the equation that's interesting is j squared equals to 1, right? And so if I look at, you know, well, that basically translates into, I mean, I can look at it different ways. I could look at it as, you know, j squared times partial squared f partial x squared equals to partial squared f partial x squared. And then using this result, this translates into, for a hyperbolic differentiable function, partial f partial y squared. So there you go. This is the sort of Laplace equation for the hyperbolic numbers. Now, the wave equation we talk about in physics is what? Partial squared y partial x squared equals to v squared partial squared y partial t squared. Is that right? I could be wrong. I think I need to put the v squared over here from dimensional analysis. See, now I've got like position squared over time squared, and then this derivative divides the time squared, and we've got a time squared down here. I think dimensionally that makes more sense. So this, you know, this right here is the wave equation for a transverse wave with speed v. So just shut up, go away, Windows. So v equals 1 for the hyperbolic numbers. If you wanted to create an algebra which had this as its Laplace equation, what do you want? If you want to use basically like time for your first coordinate, right? And if you want to use x for the second coordinate, so that's at odds with my previous lingo over here, right? But suppose I did that. Then that suggests to me that we want that to be based over an algebra with something like what? Something like oh, I'm sorry. I don't know what I want. Oh, anyway, let me stop that. I have an example in the paper we could look at for that. Let me just do that. Let me skip ahead a bit for a second. Here it is. So consider the, did I get the dimensions right at least here? Yeah, c squared uxx equal to utt. So this is a speed c wave equation, positive constant. Then I can find an algebra w sub c which takes the speed c wave equation, it's generalized Laplace equation. So I'm going to let x plus kt form a typical point in the algebra, so I decided to stick with x being the identity. I mean, you could debate whether or not that's the right choice. I don't know. Maybe. What would the difference be in terms of the calculation here if I let the time go with the identity element of the algebra? I think you could go either way, mathematically, I think. Anyway, so I want to have c squared equal to k squared in this context. And so if I look at a function f equals u plus kv, for which that, I said define gamma from wc to the hyperbolic numbers, my insight was that basically this wc is isomorphic to the hyperbolic numbers, and the isomorphism is just given by trading kt for cjt. The reason for that would be what? So I think the idea here basically is Cj corresponds to the element k that we want. And that makes sense because Cj squared is c squared, because j squared is 1. So this isomorphism assumes that we should connect k, the new thing we're inventing, and Cj, which is just a positive constant times the imaginary, so to speak, element in the hyperbolics. The imaginary unit. I'm sorry, I'm an idiot. Anyway, so if I combine, I also have a isomorphism of the hyperbolic numbers in the direct product, as we talked about last class, right? This guy. And so I can get an isomorphism, sideways TIE fighter, from my WC algebra to the direct product. In particular, here it is. If I start with x plus kt, I get x plus ct, x minus ct, right? And what does a differentiable function on the direct product algebra look like? What does it mean to be a differentiable function of r cross r? Suppose we have, f from r cross r. So here we'd say, so this is my A, so to speak. What does A differentiability here look like? What's that? Right, because we learned that the regular representation of A, well, the matrix representation of R cross R, what did it look like? A, 0, 0, B, right? So if this is equal to, partial f, partial x1, partial f, partial x2, right? What's that say? That says that partial f2, partial x1 is 0, and it says that partial f1, partial x2 is 0, which means that f1 is just equal to f1 of x1, if you allow me that abusive notation, and f2 is just f2 of x2. So a differentiable function on the direct product algebra is simply a tuple of functions of each variable separately. So that's why, okay, so this isomorphism, there's the isomorphism between the WC algebra and the R cross R algebra. And then I use that isomorphism theorem, right? The isomorphism theorem says that since WC, right, is isomorphic to the direct product algebra, that I can take an arbitrary function here. I guess I should call this big F. I can take an arbitrary R cross R differentiable function and map it back to what an arbitrary WC differentiable function looks like. And so by doing that, I get my, F from WC to WC being phi inverse composed with F composed with phi, right? So what's that look like? Here's the explicit gory detail. So so F of, and that's my typical point in the WC algebra, right? So that's going to be phi of that, which is that pair. And when we feed F that pair, it's F1 of the first component and F2 of the second component, right? Because the R cross R differentiability says it's just a function of the first and second component of the first and second component. First and second variable of the first and second. Anyway, that words. And then you take the inverse map, and you get this. So we get 1/2 F1 of x plus ct, F2 of x minus ct plus k over 2c of that. And so here's your one component function, and here's the other component function. I don't know if you guys recognize these or not, but really we're looking at nothing more than the Delamare solution to the wave equation. Remember, the Delamare solution says that any solution to the wave equation can be written as a sum of a right and left moving wave, right? And that's what these are. This is, that's a maybe left moving, that's maybe right moving. And both component functions these are both solutions of Delamare's type. But I've derived it by using an isomorphism between the natural algebra and the wave. Now this is not just mine. I found this in part in a paper by, not my approach to it, but a similar calculation by a paper by Waterhouse from like 92. So I think that's really neat, personally. All right, so the other thing I wanted to talk to you guys about today, so hopefully next time we will look at the question, applying the chain rule to look at hyperbolic conformal mapping. That's my target for all of next time. The other thing I wanted to talk about today, I'll just talk about it briefly because it doesn't, maybe we'll come back to this later and actually try to work some of them out. But the other thing I've discovered is how to calculate derivatives with respect to not just algebra variables, but also conjugate variables. And so this construction is, I was inspired by a construction of Perea, Armenta, Gonzalez, and Romero. I'm sure I'm mispronouncing all of those. My apologies. But I really do like their papers. They have a couple of them. But in this paper, they introduce a conjugate. Now, if you think about conjugate, we have a two-dimensional algebra typically, right? Like I knew from the start, like when we first started working on this, of course you know complex conjugation, and it wasn't hard to think of hyperbolic conjugation because it works almost the same. Even the formula for reciprocation works out just nice in the hyperbolic case, right? 1 over z is still z bar over z bar. It just happens that z bar can sometimes be 0 if z is a multiple of 1 plus j or 1 minus j in the hyperbolics. But then like Min and Spencer and I were like trying to factor the Laplace equation to start with. That was our initial goal. And so that kind of boils down to the question of how on earth do you find more than, like how does conjugation work in a three-dimensional algebra? And we just got stumped on it. I found this later, which is, the thing that was preventing us, I still was trying to do it in terms of a algebra variable and its conjugate, which is wrong. You need more than one conjugate. You need several. If you're working 3 dimensions, you need 2 conjugates. For 4-dimensional algebra, you need 3 conjugates. But if I have what's called an invertible basis, which by the way I explained exists earlier, we can define the Jade conjugate by just taking the variable minus twice that Jade component. That just flips the sign on the Jade component. Just it's the natural extension. This is not like the quaternionic conjugate changes the signs on the ij and the k. This is not that. This is something different. So first of all, it can calculate that here's formulas for x1 and xj in terms of the algebra variable and its conjugates. And that's just algebra, nothing. This is all in their paper too. But the one thing I did different than them was I defined the partial derivatives with respect to conjugate variables a little bit differently. So I don't know if you guys have ever thought about this or not, but in complex variables, you can go through these completely formal calculations that show you how to formulate the partial derivatives with respect to z and z bar. Like you can think about partial z being partial x, partial z, partial x, partial y, partial z, partial y, partial. And when you calculate z in terms of x, z bar is x minus iy, and x is 1/2 z plus z bar, and y is I over 2 z bar minus z. So if you calculate these derivatives formally, you know what you want to put there, right? Like partial differentiate y with respect to z. What do you get? Well, you get that minus, and you get minus I over 2, right? And so, I put a minus I over 2 here. And likewise over here, formally partial differentiating that, gives me this. And those are the partial z and partial z bar you learn in complex analysis. But those chain rules I just wrote there are totally bogus. I mean, there is no, that's an intertwingling of real partial derivatives and complex partial derivatives. Like that's not actually a legit calculation. That's why I say formally. But I thought, the right definition for the partial derivatives with respect to conjugate variables should also be motivated by such a formal calculation. And so what I did was I just followed the formal calculus, and it told me I should define partial zeta like so, and partial zeta bar like so. My definition for partial zeta is different than that found in the paper with the authors I cited at the beginning. All right. And my definition causes the calculus to work out in the completely natural way, which is that derivative of zeta with respect to zeta is 1, derivative of zeta bar with respect to zeta is 0, derivative of zeta bar with respect to zeta bar is 1 if they match, otherwise not. Different j and k is 0, and this over here is 0. If you look at their paper, they have some clutter in here. It doesn't quite work out like this. And it only works out like you want in n equals to 2, which tells me that their definition isn't quite right. Again, I'm very happy with their paper because I don't know if I'd ever thought of this without their most generous help. And anyway, here are the gory and uninteresting proofs of those, which are just rote partial differentiation, nothing that surprising. But with that in hand, the other reason I know my definition is right is because when you study the Cauchy-Riemann equations, we can talk about Cauchy-Riemann equations in terms of structure constants is one way we could do it. We could use the one I talked about to start with today, that Cauchy-Riemann equation. We could do the symmetric ones like so, all right? Those are the 3 ways, fine. But the other thing we can do, and this is really where it's at, is we could define the function to be a-differentiable if all of the conjugate variables have no dependence in f. In other words, it suffices to say that the n-1 conjugate derivatives vanish. So that, and here's the proof, and I have to do for a commutative case here. I think this might extend to non-commutative if I was a little bit more careful, but I haven't thought through it enough to be sure about that. And so partial f, partial zeta bar j, so I calculate this, right? And that's by definition that. So what's that? Well, you notice if f is a-differentiable, what do I get? This can be rewritten as partial f partial 1 times vk, which then when you commute, these two guys cancel because I have to work with an invertible basis. 1 over vk has to be defined. And so that works out the difference of partial f partial x1, which is 0. And that shows you that the condition partial fxk equal to fx1 partial fx1 times vk proves that all of the conjugate variables vanish. And actually the calculation reverses. If you have all the conjugate variables vanish, you also get that. I mean, anyway, it's if and only if, I'm pretty sure. Although I've stated it as if then, but I think it's actually interchangeable. So if you guys you guys have had complex analysis, or who has not? You have not? So one of the things you learn in complex analysis is that for a function from C to C, one way you can define it to be complex differentiable, or what's later called holomorphic, is if the partial derivative of f with respect to z bar is 0. So eventually you learn in complex analysis a complex differentiable function is sort of just one which is just a function of the complex variable z, but not z bar. So with that insight, when somebody asks you, hey, is the function z times z bar complex differentiable? You're like, no, it's got a z bar dependence quite clearly. You know, somebody asks you, is the function f of z equal to sine of z plus z cubed plus the exponential of z squared minus 3 sine z? Is that a complex differentiable? You look at it, you go, yeah, it's just a combination of functions of z. So that way of thinking, still true in the A calculus, provided you define conjugate variables in the proper way, as I show here. But I was very, very happy with this because it's not just for not just the complex case. I mean, this is for any associative finite dimensional real algebra. And here's a generic example of a function which is not A differentiable. You just take the function zeta times the second conjugate that always exists in any 2 or higher dimensional algebra, and it's it's only A differentiable at the origin, I think. Yeah, that's it. This is the standard example in complex analysis, z times z bar, for a not differentiable function. Now, the kicker is that you can actually also, just like you can do with complex variables, you can calculate partial z and partial z bar in terms of partial x and partial y. You can do the same in A calculus. You can invert these definitions and solve for partial x1 through partial xn in terms of partial zeta and partial zeta bar 2 through zeta bar n. For example, in the 3 hyperbolic numbers, I can work out that partial x is the sum of these algebra derivatives. Partial y is the sum of these algebra derivatives, and partial z is the sum of these algebra derivatives. How to actually calculate that? Well, that's an interesting problem. Maybe that would be a good homework problem for you guys. I need to come up with some homework problems for you guys. I'll get there eventually. At the moment, I just want you to read my paper so we can get everything out in the open and try to solve some interesting problems. So I'm trying to do that as fast as possible. So anyway, long story short, if you look at these, which by the way, these are the Laplace equations for the 3 hyperbolic numbers. This one, for example, you can see this as the equation 1 squared minus, suppose y connects with j, z connects with j squared. So what's this? This is like the equation, this is the differential equation corresponding to 1 minus j times j squared, which is j cubed. So 1 minus 1 is 0. So this hitting a function being 0 is the Laplace equation for the 3 hyperbolic numbers, which corresponds to the equation 1 minus j times j squared being 0. This one corresponds to, what's that? That's j squared minus j squared times 1. Well, j squared minus j squared is 0. Yay. But that actually means a non-trivial partial differential equation when you sort through the reverse implication to the PDEs for the component functions. And likewise, this one, well, that's j squared, which is actually j to the 4th, which is, by the way, also j. So j squared minus 1 times j. Well, that's j minus j, which is again 0. But here's the other more beautiful, I mean, this all works together. When I actually calculate these guys and put these real partial derivatives in terms of algebra partial derivatives, what happens? I get this expressions, which are really, really quite pretty, because you notice everything has a naked derivative with respect to a conjugate variable. Here, 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 and here. So if you think about it, if you've got a function on the 3 hyperbolic numbers, which all of the conjugate variables vanish, you hit it with these differential operators, it automatically goes to 0. But of course, that has to happen because a function that is 3 hyperbolic differentiable necessarily solves the Laplace equations. So this is the tip of an iceberg of something I don't completely understand yet, which is what I really want to do is I want to take real partial differential equations and I want to convert them to algebra differential equations and solve those, like calculus over an algebra, which is easy. But the question is, when is it nice? I have no idea. I can reverse engineer stuff, but I don't have a, so we'll keep coming back to that question. I'll keep trying to restate that question as we go on. Maybe we'll get somewhere. I don't know. All right, so next up, I will try to get out the paper by Motter and Rosa, which actually shows for a specific hyperbolic transformation, the hyperbolic conformal transformation corresponds to a uniformly accelerated rod. And so he solves the wave equation on the uniformly accelerated rod, looking at the hyperbolic numbers like being space-time. So I'm going to try to read that paper before Wednesday and see if we can't like just attack it. Right, so I'll try to send you a copy of the paper, guys, in case you want to read ahead and or just have a copy of it to stare at with me. But thanks, guys. I'm sorry, I seem to have gone over. That may be a theme for this semester. You can hit the button so I can say